Good evening, everyone. I'm Anish Shambekar, PMRF and PhD candidate from Aerospace Engineering IISc Bengaluru. Welcome to this week's live interaction session for the NPTEL course Dynamic Behavior of Materials. The course code is NOC24ME102, and in this session, we'll be covering the content which has been instructed for week 10. So, taught in this. An outline of what all was covered in this week is given below. We first start off with a few dynamic deformation examples. So what does this dynamic deformation mean? Dynamic, if you look at the words, dynamic would refer to something that is changing with time, whereas deformation would refer to change of material configuration. So if you have a collection of particles, we will call that as a body, and then the material body will undergo some deformation, which means whatever configuration in which the particles have been arranged, that has been changed. Suppose like you have elongation, then each you can say that or every particle has moved along one particular direction. So dynamic deformation, the word suggests changing material configuration with time. And how do we determine this? How do we quantize this? We use so the critical parameter here to judge dynamic deformation would be strain rate. This is the strain rate. So we'll go through a few examples just to get a flavor of what all is happening. So in the first example is of a rod. So a thin rod, so an approx 1D object, fixed at an end, and another end is being pulled up with some velocity V naught. The initial length of the rod is L naught. Then we can define the strain rate to be epsilon dot is delta epsilon by delta T. Delta epsilon we can write as epsilon at time equals T minus epsilon at time equals 0. Epsilon at time equals T equals the deformation is roughly delta L by L naught minus 0 by L naught, which is delta L by L naught. Similarly, delta T is nothing but delta L upon V naught, which is the time required for the object to move up. From this, we get epsilon dot delta L by L naught upon delta L by V naught, which is V naught by L naught. Assuming V naught to be say 1 meter per second and L naught to be 10 centimeter, which is 0.1 meter, you get epsilon dot equals 10 second inverse. So very simple example. Another example could be, suppose you have a thin rigid cylinder, not rigid, thin cylinder, deformable. It's moving ahead with a velocity v naught, time t less than 0. At time t equals 0, it impacts a rigid boundary. Still, majority of the particles will be moving at v naught except the end which contacts, except the particles at the bottom end, which will be contacting the rigid boundary. As a result, you have deformation in the boundary. So you have a deformation delta L happening at t equals delta t. Again, you can write, we can write delta epsilon s, epsilon at delta t minus epsilon at t equals 0, which is delta L by L naught, assuming sufficiently small uh, delta L. Delta T we have to determine. So how do we do that? We use kinematic equations. If you remember, we have three kinematical equations of kinematics, and if we do this by assuming constant deceleration. So if you remember, there is this thing which goes as final velocity square is initial velocity square plus 2as, which gives 0 square is the final velocity is 0, initial velocity is v naught plus 2 acceleration delta L, which gives acceleration A is equal to minus v naught square by 2 delta L. We also have first equation of kinematics as v is equal to u plus at. Substituting v equal to 0 and u is equal to v naught plus minus v naught square by 2 delta L into delta t. From this equation, we end up getting delta t is 2 delta L by v naught, which gives us epsilon dot is equal to 2 delta L by v naught. Sorry, uh, delta L by L naught into v naught by 2 delta L. Delta epsilon by delta t, which gives us v naught by 2L. Assuming, say, L naught is equal to say 5 centimeter and V naught, or basically a 2-inch projectile hitting at 1000 meter per second, which will give us epsilon dot is equal to 10 raised to 4 second inverse. So this is roughly the plastic deformation. Third example, if we have shock wave. So suppose you have a shock wave such W for short through copper at 30 GPa pressure, right? So the shock front would look something like US is the shock speed. If I draw pressure versus distance plot, if we assume like a thin shock front, delta S is equal to 5 micron, a thin shock front, and P is 30 GPa, which means again you can look into the material data for shock waves. I think table 4.2. V by V naught, which is the relative reduction in volume, is 0.863. Therefore, epsilon and shock wave velocity is 4950 meter per second. Delta epsilon, as you have seen, is nothing but delta L by L naught minus 0 by L naught, which is delta L into area upon L naught into area, which is V naught minus V upon V naught, which is 1 minus V by V naught, nothing but 0.137. And delta T is nothing but shock wave velocity, shock width upon shock wave velocity. This is 5 into 10 raised to minus 6 upon 4.95, 10 raised to 3. So which is of the order of 10 raised to minus 3. Then if we take epsilon dot delta epsilon by delta t, it turns out to be minus 0.137. 0.037. I'm just writing the magnitude into 4.95 10 raised to 9 by 5, which is around 1.4 into 10 raised to 8 second inverse. So this is for the shock wave. Using these three examples, not exactly using these three examples, we have a general classification for different dynamic deformation phenomena based on the strain rate. So the typical values associated with it are epsilon dot 10 to the power 10 to the power 5 7 second, everything is second inverse. Phenomena is shock wave. If epsilon dot lay in an intermediate strain, then you have got a plastic wave. If epsilon dot is even lower, you have an elastic wave. What happens if you have a quasi-static loading? S to minus 5 to 10 is to second inverse. This is a quasi-static case. And 10 is to minus 8 to 10 is to minus 5 second inverse. This is the viscoplastic response. So the top three are basically your inertia effects are important. Okay, so this is a rough outlook of the same. Next up, we have the effect strain rate has on materials. So generally speaking, generally speaking, strain is a function of stress is a function of strain rate, and temperature. Here we are assuming that sorry, not assuming. Here we are looking at only deformation as a function of the current state of material. So stress is developed only based on current deformation, which is strain, your current strain rate, how fast it's being deformed, and the temperature. How this looks out in practice can be thought of in the following graphs. First, you have a stress strain curve. You have a stress strain curve, which is a compressive stress strain, and this is for the aluminum 7075 T6 aluminum. What do we see is for all the different strain rates, there is no variation in response due to strain rate. Next up, if we look at different material now, which is titanium 6, aluminum 4, vanadium, it's an alloy. Again, compressive stress strain curve. What do we see is should be all of the yield point in the diverge. Something like this. Right, so three branches with increasing strain rate. Titanium 6. And here epsilon dot belongs to 0.004 to 2 second to 20 second inverse. Another plot for a stress strain curve for another material. This is pure titanium. Pure titanium. So for this, you see, this epsilon dot is equal to 0.001, epsilon dot is equal to 3.9, epsilon dot equal to, this is 7600. So here we see that there is a then it goes to a particular strain and then stress falls down for lower strain rate values. Whereas the peak strain that it achieves beyond a particular for a very high strain rates seems to be decreasing. So the peak stress has increased, but the maximum strain it can go till has seemingly decreased. Another in this series of stress strain plots is tantalum. The one is 0.0008, above is 0.008. Then you have something that goes even above, which is 3500. This is for tantalum. In general, it is it's considered impossible to predict behavior of the material right from the first principles. So one more plot of interest is stress versus strain rate curve. This is a log plot. So if you consider how stress increases for different strain rates, should write the strain. I'll write a log scale here. This is 10 to the power 5. And this is gamma equals 0.15, gamma equals 0.10, gamma equals 0.05. This is for the case of 1100 aluminum. We see here in this plot that when shear strain rate is larger than say 10 to the power 4 or 10 to the power 5 second inverse, the stress increases rapidly. Dramatic hardening is seen, and this is generally not accounted for in popular constitutive models. It ends up requiring a lot of special modifications to the model. Another practical pointer here is that as your strain rate increases, material deformation progresses from fully isothermal to fully adiabatic. So this full adiabatic process can in turn give rise to certain instabilities within the material, shear instabilities, which we'll look at in following week lecture. So we talked about what consists of dynamic, what we mean by dynamic deformation, and we talked about certain trends that we see for different materials. It was noted in these different materials that you do not have necessarily a uniform trend. In general, you can have you have we have seen specific examples of material, specifically 7075 aluminum, which does not seem to be affected by strain rate. Whereas on the other hand, you have uh, say titanium 6 aluminum for vanadium, which does seem to be affected by strain rate, where increasing strain rate leads to an increasing flow stress. And we also saw this dramatic hardening, which happens for higher strain rate conditions. So, how do we arrive at all these cases where we look at uh, how do we test out different materials? That's an important question. So, the first type of testing that we are going to look at is the compressed gas machine. Remember that our aim is to see how stress varies with strain, or stress varies as a function of strain and strain rate both. So compressed gas machine looks like there is usually a piston with an angle. That piston is cocked in its position. There is some pressurized gas flowing around. Casing. Then casing. Some pressurized gas in between. And then there's a specimen. Specimen. So all settled on a track. Specimen. And how it works is specimen undergoes compression. It's placed on a machine handle. There's a movable piston in the system. It is cocked in place with support jocks, and it's accelerated downwards. An auxiliary pressure reservoir. Auxiliary reservoir is pressurized after support chocks are lowered. As a result, the specimen is impacted and undergoes compression. Right. So this is you as accurately as you can. You control the pressure, then move the piston. The piston will move it forward with some velocity, and it will piston mass is sufficiently large so that there is no significant deceleration involved upon impact with the specimen. Then the specimen will undergo compression, and you can figure out what uh, opposing loads, sorry, what resistive loads act on the specimen to oppose its compression. Pressure bar. Well, it's particularly useful for epsilon dot varying from 10 to the power to 10 to the power 2 to 10 to the power 4 second inverse, and its basic configuration is that related to compression testing. So you have got a striker bar which moves ahead with some velocity v. Then you have got the incident bar, small specimen, and you have got reflected bar, sorry, transmitted bar. There is usually a momentum trap somewhere here to take away some of the energy. I'll also draw this dotted line. This is called as the striker bar. This dotted thing is your pulse shaper. We'll come to that in a moment. You have got a strain rate here on your incident bar. And it has some properties of area, uh, this and C naught. Right. Another dotted line here. Next up, you have another strain gauge for the transmitted bar. So, if you look at how strain stress varies as a function of time, you would have something like this, some small oscillations. These, if you remember, are the Pochamer shocks, and they are related to edge effects associated with the rod. So, the rod has a finite thickness, it's rather particularly thin, and there will be some edge effects associated with that. This pulse shaper and the other strain gauge, right? These are used particularly for brittle materials. What pulse shaper is basically, it's usually made out of copper, and it plastically deforms, therefore increasing the rise time. And The strain gauge and the pulse shaper are used particularly for brittle materials. As a result, you end up getting a stress pulse, which has a longer rise time and ends up becoming more smoother. Okay, we'll now label the two ends of the. This is the end one. This is end two. Right. So suppose V1 and V2 are the velocities at interfaces 1 and 2 respectively. So one more thing that you have is your specimen has a lower impedance than your bars. So this is specimen. This refers to the reflected, sorry, incident and transmitted bar. So you have greater impedance there. So the same stress would lead to smaller velocity values. Right. So V1 greater than V1 of t, if V1 of t is greater than V2 of t, which means the first interface 1 moves faster than the second interface, then what you have is specimen of length L size decreases with time, and the specimen will undergo plastic deformation. Epsilon dot time t can be written as d epsilon by dt. If you refer back to the very first example that we considered, where we took a rod and fixed one end and moved the second end with velocity v naught. So you have basically the same condition where you have the relative velocity of the two ends v1 minus v2 of t divided by the current length. Also, for a bar, we have sigma is equal to E epsilon, and sigma is nothing but rho up c naught, rho naught up c, rho up c, c being the speed of sound in that medium. It's nothing but rho up root of epsilon, which is up root e rho, which means epsilon root e by rho is equal to up, or epsilon into c gives us up. So this is strain into speed of sound in that medium gives us the current particle velocity. At t equal to 0, we have no reflection, no reflection, which means V1 is equal to C naught epsilon I, V2 is equal to C naught epsilon T. Epsilon I is the incident pulse strain, epsilon T is the transmitted pulse strain, epsilon R is the reflected pulse strain. Yeah, so at t greater than 0, your V1 is C naught epsilon I minus epsilon R. Therefore, epsilon dot is equal to d epsilon by dt. ends up becoming C naught epsilon I minus epsilon R minus epsilon T upon L, which means epsilon as a function of T. For the overall, we are talking about for the specimen, right? The specimen deformation. C naught by L integral epsilon I minus epsilon R minus epsilon T dt from 0 to T. This refers to the strain of the specimen. Okay, and for stress in the specimen, we have sigma is equal to P1 of T plus P2 of T by 2A. A is the specimen area, and P1 and P2 of T are forces at ends 1 and 2. It's important to note here that note we do not consider wave propagation inside the specimen, and the reason for this is when wave enters in, there are reverberations, and in about 3 reverberations equilibrium is reached. So the pulse width of the wave is sufficiently large so that we can bypass those reverberations and take the overall deformation. It takes a bit of time for the actual equilibrium of the rod to be reached, of the specimen to be reached. But as we said here, that it takes about 3 reverberations, so it's a very short amount of time compared to the pulse width, which means we can approximate it using the equation that we have chosen here. We can write stress as function of strain and area A naught epsilon naught epsilon I plus epsilon R, and P2 of T to be A naught epsilon naught. Again, A naught and epsilon naught refer to the incident and transmitted bars. We are simply multiplying their strain values with their area and modulus to obtain forces on the two ends of the specimen. So these are the forces measured incident and transmitted bar. With this in mind, we can write the stress inside the specimen as A naught epsilon naught by 2A epsilon I plus epsilon R plus epsilon T. Again, for equilibrium, you must have E1 of T equals P2 of T, which means for epsilon I plus epsilon R should be equal to epsilon T, which gives us epsilon dot T is equal to, going back to this equation, you get epsilon epsilon T is nothing but epsilon I plus epsilon R. We end up with minus 2 C naught by L integral 0 to T epsilon R of T dt. This is how the strain rate of the sample looks like. So this is for the strain rate of sample, strain rate of specimen. This is for stress of the specimen. And strain rate is nothing but minus 2 C naught by L epsilon r. This is the strain rate of the specimen, which means you have got sigma epsilon dot for the specimen. So in these three equations, we know A naught, E naught, which is the area and modulus for the incident and the transmitted bar. We know C naught, which is the speed of sound in those bars. We know L, which is the initial length of the specimen. We know A, which is the capital A, which is the area of the specimen. So using the three strain gauges, or sorry, using the two strain gauges, we know both epsilon I incident strain while the wave passes through, and after it comes back, we know the reflected strain. Actually, we know the combination of epsilon I and epsilon R, but from that we can figure out the reflected strain. We also know the transmitted strain. So what happens is you basically know everything as a function of time. Now all that is left is for you to integrate epsilon of t versus time. Okay. This was for the compressive configuration, but split Hopkinson pressure bar can also be used in tension, torsion, and shear configurations. You can look at there are multiple like creative ways to address that problem of how to get the other configurations. You can look say in the reference book itself. That's a good source to look at what different types of configurations there are. Next up, we'll have a look at plastic deformation. So as we mentioned at the beginning, in general, stress is a function of strain, strain rate, and temperature. In case a material undergoes plastic deformation, there is an irreversible change in the material. So there will be some amount of residual deformation that is left back, that is left behind, even when the material is unloaded. So it's an irreversible phenomena. This makes it therefore a path dependent process. So because it's a path dependent process, deformation history becomes important. This is because of basically the deformation substructures created. So as a result, you end up having a function with liquid stress as a function of strain, strain rate, temperature, deformation history. Normally, to those of you who have looked into solid mechanics or even done a strength of materials course, you must know that stress and strain in general are tensors. So what we do here, or what we mean here, is we basically substitute stress or strain with their effective values using a scalar by constructing a scalar effective value for the stress as well as the strain using their using the principal values. So on the principal axis. So another point is that in metals and polymers, plastic deformation occurs due to shear stress and shear strain. So we have already seen the deformation mechanisms involved. Slip being a primary one. Finally, an experimental data yield stress versus log of strain rate, shear strain rate. So, so this is a plot for lower yield stress for mild strain. You have got different temperatures: 195 Kelvin, 225 Kelvin, 243 Kelvin, 493 Kelvin, 293 Kelvin, 493 Kelvin, and so on. This is a plot of lower yield stress plotted as a plotted versus logarithm of shear strain rate. From this, we see sigma y increases with gamma dot. This is usually seen for all materials. But the other thing that we also see here is sigma y increases faster at lower temperatures. Uh, so you can see what we have is in terms of plastic deformation, what we have stress as a function of the yield point, yield stress as a function of strain rate. Even that itself has a trend even that itself has a trend both in terms of the rate of deformation, shear strain rate, or your temperature. So to understand materials, because we are interested in once we understand the materials and we are interested in studying their dynamic deformation, an important point along the way comes in the form of constitutive relations. These are important so that we can use an empirical knowledge, package it into a constitutive relation form, and then use that analytical expression to relate deformation of the material with the resistive load that the material will apply, with the load that the material will try to resist that deformation. This is important in because as we go into say designing different structures and we are interested in how exactly the material deforms, this is where the material information is packaged neatly in the form of an empirical constitutive relation. So usually you have at low strain rates, you have at low and constant strain rates, we have sigma is equal to sigma naught K epsilon raised to n. This is basically your work hardening expression. We've already seen this in previous weeks' lectures. Also, if you look at the effect of temperature, then on flow stress, your sigma is equal to sigma r 1 minus T minus Tr upon Tm minus Tr whole raised to m, which I can write as sigma r 1 minus T star whole raised to m. So sigma r refers to a reference stress, Tm refers to melting point, Tr refers to reference temperature, sigma r is reference stress. One more important observation is that strain rate affects flow stress as directly proportional to logarithm of the strain rate. And this direct proportionality between flow stress and logarithm of strain rate is seen even when the strain rate isn't too high. So combining all this, suppose I were to plot, I'll give a couple of plots here. See yield stress again as a function of temperature. Then epsilon dot is equal to 0.003 second inverse. So you can see that it follows that 1 minus t raised to t star raised to n sort of path. Another is for yield stress as a function of logarithm of strain. So you have got something like 77 Kelvin, 143 Kelvin, 290 Kelvin. So these plots basically show us the effect of temperature and strain rate on Boreal stress for FE. Using the above trends for the Bohr hardening, for the effect of temperature and for the effect of strain rate, we can combine them together to create uh, a like a combined model. So basically, that is the popular Johnson-Cook model, wherein you write sigma naught plus b epsilon raised to n 1 plus c ln of epsilon dot by epsilon dot naught and 1 minus t star raised to n. It works well for a here b c sigma naught n and m. These are experimentally determined constants, and what you have is this Johnson-Cook model could say even substitute epsilon dot not to be reference standard to be 0. This Johnson-Cook model, it works well for a number of metals, which is why it's a popular choice in modeling deformation in metals. So the final part that we looked at is something related to the microstructure of the material, particularly dislocation dynamics. So here, before we begin, it's important to write restrict ourselves to dislocation motion resulting in plastic deformation. So an example, we could think of an edge dislocation. Suppose there is an edge dislocation here. We apply a shear load. You can see that the dislocation will move ahead. So dislocation moves due to applied shear stress and the edge dislocation. This is basically an edge dislocation that we are talking about here. And suppose the Borges vector associated with it B then the force on the dislocation per unit length. This is assuming ideal orientation, like the one that we have shown here in the diagram. It is F is equal to tau into P. And these the dislocation versus, and here you have frictional forces prior to resist dislocation motion, which is why in the first place you need an external force. So we can write this force per unit length in vector form as F is equal to inner product sigma B cross product with L, where L is the vector parallel to dislocation line. Now suppose instead of a single dislocation you have a number of dislocations. So I'll draw a diagram like this. Length and L, shear load is applied. What happens is we'll have different steps. So different all the edge dislocations you can assume they have moved forward. So again it's an ideal arrangement. Theta is the angle. Gamma is equal to tan theta shear strain, approximately equal to theta for small theta. Gamma is, sorry, just write gamma is equal to tan theta, which is n into B upon L. I'll just write down what this means. N is the number of dislocations. So in this diagram, you can see that we have got 5 edge dislocations, all in an ideal arrangement, stacked on top of each other. So I can write N by L square to be L. N by L square we can refer to as the dislocation density. Rho. So your strain is equal to dislocation density into Burgess vector into side of this. Taking time derivative, you can think that the dislocation density rho will be it will be constant, it will be inherent to the material depending on what its microstructure is, how it was found. So you have got gamma dot T gamma by dt. It's equal to gamma dot, it's equal to rho b into v. Gamma dot is equal to rho b. This v refers to how fast the dislocation moves ahead. So the dislocation velocity. And another thing is that this gamma strain rate can be converted to epsilon strain using an orientation factor, which is called as M. Orientation factor refers to average value It's derived from rather the average value that minimizes deformation energy. So we end up getting m epsilon dot is equal to 1 by m gamma dot 1 by m rho bb. Value of m can be 3.1 for FCC and 2.75 for BCC arrangement. Given in general, you have a crystal with for a crystal with multiple slip systems. You have epsilon dot p summation k is equal to 1 to 1 pk ok pdk or vk times mk plus s. K is equal to 1 to n refers to the number of slip systems. Already seen slip systems consist of a slip direction and a slip plane. And the now what we have is this will we are interested in looking at the dislocation velocity v. So the dislocation velocity v depends on stress, applied stress. A few formulations for the same have been given. So one of the first one was the Johnston-Gilman formulation. Dislocation velocity is proportional to sigma raised to m applied stress raised to m into exponent of minus e by kt. So there is both a term for the applied stress, some factors involving enthalpy of activation, some energy of activation, and the temperature. Another model is the Rode model, where V is given by kt by h. So this is basically your attempt frequency into k, k being some numerical constant capital K, exponent of minus delta h by kt. Delta h is the enthalpy of activation, exponent of b times Ta minus tau a minus tau l by kt. So you have an attempt frequency of a constant, you have enthalpy of activation. B stands for activation volume. Tau a refers to applied resolved shear stress. Tau L refers to long range stress, long range internal stress. But a third model, which is more uh, in line with what we see, is the Gilman model, where he writes dislocation velocity is equal to Vs star 1 minus e raised to minus tau by s. That's Vd star e raised to minus d by tau. D refers to the characteristic drag, and Vs star Vd star referred to, these are basically your limiting velocities. So as tau goes to infinity, equals Vs star Vd star. It's an upper limit. on V that isn't there in the above models. So which is why this third model makes more sense, because as we have already seen in the, I think, week 2, the very earliest weeks, that whatever, even if deformation that happens, it cannot move faster than the shear wave velocity. For moderate stress, we can take dislocation velocity to be proportional to the shear stress. As a result, force becomes tau into B, which is m into A using Newton's second law. M refers to the effective mass of dislocation. As in, what happens is, suppose the dislocation velocity is proportional to the shear stress. What will happen is it will have some acceleration, there will be some effective mass and some non-zero acceleration. As a result, your dislocation velocity will keep on increasing and it will just not stop. So what this would mean is, for a given applied stress, you will just keep on, as you keep on increasing stress, your dislocation velocity will just keep on increasing. This is not physically possible, because otherwise this very crude analysis predicts that dislocation velocity can end up to very large, uh, near infinite, very large values. So you need some sort of mechanism to stop it from, to hold back this dislocation velocity. You can think of it, there are two ways. First is, if somehow the effective mass that we are defining, if somehow there is some change to that as a function of velocity, but mass keeps on increasing, then you'll never reach a very high velocity. And another thing is the drag stress. If similar to like in fluids, if suppose there is a drag stress, as the velocity of this dislocation increases, the drag force also increases very rapidly. And again, that also ends up acting as a barrier. So if one were to plot how dislocation velocities, log of dislocation velocity versus log of the shear stress. Oh, sorry, log of applied, this is the result tau RSS, result shear stress. So you could say something like this for molybdenum, something like this for another material, something like this for lithium fluoride with an edge dislocation. Similarly, a different path for lithium fluoride for a screw dislocation. So there seems to be an upper limiting value to the instructor's knowledge. There has not been reported a dislocation velocity moving faster than the shear wave velocity in the medium. We also see that as the velocity increases, your slope decreases. So it automatically starts limiting itself. So roughly speaking, we can draw a schematic diagram which looks like this. Log of dislocation velocity versus log of result shear stress, RSS. You can divide it into three zones, so to speak. First one is zone 1 where the slope is less than 1, zone 2 where the slope is equals 1, and zone 3 where slope is less than, greater than 1. This is the V shear, which is the limiting velocity. And we can write three regimes are seen in this plot. So I think this is specifically for nickel maybe, but in general this is how it's seen. And we also see that the dislocation velocity is less than elastic shear wave velocity. So the first region is called as the thermally activated dislocation motion. Region 2 is called as phonon drag. Region 3 corresponds to relativistic effects. For the thermally activated dislocation, I'll just have one small point. So suppose this is your material. This is my dislocation. And if this is the shear stress that is applied, you can see that there is some in-plane resistance to the dislocation motion. And that in-plane resistance we can plot as a force versus distance plot. You see, this is schematic, but you would see something like a sinusoid whose amplitude is tau pn. Tau pn refers to the this is a naught, which is the lattice parameter. Tau pn refers to the pulse ERL, pulse Nabarro stress, and what this is as the shear stress basically tries to move the dislocation forward from one equilibrium to another, which is why the lattice parameter A naught is shown here. And initially, some resistance is required to overcome this. Some material, surrounding material will provide resistance. To overcome that, some external force is needed, and a particular energy barrier needs to be crossed over. Then this only happens when the resolved shear stress greater than the pulse Nabarro stress leads to motion. Motion leads to dislocation motion. Another thing is that there may be some out of plane resistance to the dislocation. Suppose you have a dislocation, not necessarily a straight line, which is trying to move on this plane. There may be forest dislocation, which makes so it's usually perpendicular to the slip plane and acts as a barrier for dislocation motion. Okay, so this three regions that we saw earlier in this will be continued even more: thermally activated dislocation motion, phonon drag, as well as relativistic effects in the upcoming week's lectures. So through all this content, we have covered most of what has been taught in this week, and I hope that some of this helps you understand what's happening. If you have any doubts, we can take them now. If not, then we'll call it a day. Thank you for attending this online or watching it on YouTube. I'll see you again in the next one.